Lesson 3.10, Linear Approximations and Differentials. Essential question, can I approximate an output with linearization? All right, let's take a look at a curve and its tangent line. The tangent line is referred to as the linearization because it's a line. And the tangent equation and the curve are exactly equal to each other at the point of tangency. And their approximations to each other are very close. The closer you are to the point of tangency, the better the approximation. The farther away, then you can see right here that the values, the output of the linearization, the output of the curve, have a greater difference between them. Okay, let's find the linearization of the function at a equal to 1 and use it to approximate these different values. Okay, so let's go ahead and take the function, which is y is equal to root x plus 3, take its derivative, which is this, and then evaluate it at 1, and this will be the slope of the tangent line. Okay, now I know that the point of tangency is 1, 2, so I'm going to write the equation of the tangent line. I'm going to isolate y, and that y is what we call the linearization. All right, so this is the linearization right here, and here is the function. And what we're going to do is we're going to find these values of the linearization and the actual y value for points before 1 and after 1, because we know these values are very close. And if you look at them, they're very close. At the point of tangency, just as we would expect, they're exactly equal to each other. And again, the farther you get away from 1, the bigger the difference that we're going to have. Okay, what is the linearization of f of x equal to e to the x at x equal to 1? This is a typical AP question. Go ahead and try it, stop the screencast, and then I'll show you the answer. Okay, here's the answer. The function is y equal to e to the x. I'm going to find its derivative, e to the x, and then I'm going to evaluate it at 1. Now, the point of tangency is 1, comma e. So I'm going to use that point and this slope in my point slope formula, solve for y, and then I isolate y, and then I get this. So that's my linearization. Okay, let's try again. Use the linearization to estimate root 105. Stop the screencast and see if you can do it, and then look at my answer. Okay, so here's the function, and the point of tangency is 100. If I put 100 here, the output is 10. I find the derivative, I evaluate the derivative at 100, and this is my slope. So now I have my slope, and I have my point. I can go ahead and find the equation of the tangent line, solve for y, and this is my linearization. Now, they say to use the linearization to approximate 105, so I'm going to put 105 into my linearization, and I'm going to get 10.25. And I know that's an approximation, but a darn good close one. All right, let's take a look at this one. This comes from an old AP question. Let f be the function. The tangent line at x equal to 2 is used to approximate. Which of the following is the greatest value of x for which the error resulting from this tangent line approximation is less than 0.5? All right, let's go through the steps. We have to work with the function, find its derivative, find the value of the derivative at 2, and then get our linearization. So here's our linearization, and here's our function. I went ahead and drew a picture of the quadratic, and I drew a picture of the linear. And you can see at 2, this is where they're exactly equal to each other. And the farther away you get from 2, the more apart they become. Now, this is what the question is asking. When the error is less than 0.5, in other words, this is the error right here. Okay, the error between the function and the linearization. When is the difference between the function and the linearization is less than 0.5. So let's go ahead and do that. So the function is this, x squared minus 2x plus 3. And then I'm going to subtract the linearization, which is 2x minus 1. And I want that to be less than 0.5. So now I'm going to have x squared minus 4x plus 4 less than 0.5. And then I'm going to use my calculator to approximate that. And when I use my calculator, I am going to get x is going to have to be less than 2.707. And the best answer there is here. So it's a good thinking question on this one. All right, let's talk about differentials. Differentials are right here, this picture. This is a differential. It's the change along the tangent line. The change along the curve is actually delta x. It's the true change. This is the change along the tangent line. If you think about dy dx equal f prime of x, and you think of these as separate entities, you can multiply dx on both sides, and this is what we're getting. So the differential y is defined to be the instantaneous rate of change at a particular point times the differential of x. And differential of x is the same as delta x. All right, let's go ahead and do some problems. We want to compare delta y with differential y using this function and look at changes from 2 to 2.05. All right, so here's a picture of the curve in blue, and here's the tangent line. And we want to see the difference between true change and differential change. All right, so I need to find a derivative, which is f prime of x, and then I need to find the derivative at 2, and that's 14. Okay, so right here is dy dx equal to f prime of 2, and then I'm going to move the dx over. This is my differential. I just want you to see where it comes from. Now f prime of 2 is 14, and my delta x is right here, the difference between 2 and 2.05, so that's 0.05. And then so this value is equal to, let me go ahead and 0.05 times 14, and that answer is 0.7. Okay, now let's go ahead and find the true change between these. And the true change, if you put this in your calculator, you're going to find that equals 0.717625. And what you need to see is they're very close to each other because 2.05 is very close to 2. So you do about the same thing and you do part B now. Same idea, but now we're going to get a little closer to 2 and see the difference between the true change and the differential. And here is the answer. The true change was 0.140701, and the differential is here. The closer and closer we get to 2, the more these look so much alike. Okay, here's another typical AP question. Go ahead and stop the screencast, see what you can do. And here's the answer. I went ahead and I wrote dv dr is equal to v prime of 10, and then this way I can get my differential. And the differential is the derivative at 10, and then our dx, or differential x, is going to be 0.02. Now, how do we get the v prime? Let's go over here. Here's the volume of a sphere. Here's its derivative. Evaluated at 10. 10 is the spot where we have the tangent, point of tangency, and then we get this 400, and that's where I got it from right here. And so the answer is 25.133, so this would be your answer. All right, here's another problem. Go ahead and stop the screencast, see what you can do, and I will reveal the answer. And here's the answer. You want to set up the differential. Differential A is equal to the instantaneous rate of change times differential R. Here's the equation of the area. Here's its derivative, and here's its derivative at 10. 10 is the point of tangency. This is the slope. And we're going to put this right into here, and we'll multiply by 0.1. We're going to get 2 pi, and that's the correct answer. In our book, the author does this problem. He does this with a sphere. We've been doing sphere all along. I just want you to see all the similar things that we've been doing. Here's the formula. You want to take its derivative, and you want to write the differential equation like this, and then identify the point of tangency at 21, the differential r, put those into these quantities, and you get around 277. Again, this is the change along the tangent line, and it's very close to the true change.